One of the biggest and perhaps the main scientific achievements of the last century was the discovery of the expansion of the universe. Distant galaxies are moving away from us and each other faster than those that are closer, and it seems as if the fabric of space itself is stretching on the largest scales. The density of matter and energy in the universe is decreasing over billions of years and shows no signs of stopping. If we look far enough, we can see galaxies moving away from us so quickly that even if a spaceship were sent towards them at the speed of light today, it still wouldn't be able to catch up. However, all of this doesn't quite fit within our imagination. As you may already know, in the distant future, our Milky Way and the Andromeda Galaxy will collide with each other and form a single, shared galaxy for the Milky Way. This raises the question, if the universe is expanding, then why are galaxies colliding? When Newton first thought about the universe, he imagined space as a grid, an absolute and fixed entity filled with masses that were gravitationally attracted to each other. But then came Einstein. He realized that space was not a fixed, absolute grid like Newton imagined, and it did not resemble the static grid of Newton's conception. Instead, Einstein saw space as a fabric that was curved, distorted, and changed over time due to the presence of matter and energy. Moreover, it was precisely matter and energy that determined its curvature. However, if space-time contained only a collection of different masses, they would inevitably collapse and form a black hole. Einstein did not like this idea, so he added a correction in the form of a cosmological constant. If this additional term exists in the equation, it implies additional energy permeating empty space, which can repel all of these masses and keep the universe stationary. It would prevent gravitational collapse and allow Einstein to imagine the universe as almost static and eternal. The idea of a static universe was appealing to some scientists, but not to all. Russian physicist Alexander Friedman showed that if one does not add this cosmological constant and fills the universe with energy, matter, radiation, dust, and sinkha, there exist two classes of solutions, one for a contracting universe and the other for an expanding one. Mathematics gives us a possible solution, but we need to look at the physical universe to determine which one describes it. This happened in the 1920s thanks to the work of Edwin Hubble, one of the most influential cosmologists of the past century. Hubble was the first to discover that one could measure the characteristics of individual stars in other galaxies and determine their distance by combining these measurements with the work of astronomer Vesto Slipher, who showed that there is a shift in the atomic spectrum of these objects. He obtained an astonishing result. Either the theory of relativity is wrong, and we are at the center of the universe, with everything symmetrically moving away from us, or the theory of relativity is correct, Friedman is right, and the further a galaxy is from us, the faster it is moving away from us. With one movement, the theory of the expanding universe moved from a simple idea to a leading description of the universe. This is a highly complex and difficult process, filled with various physical and mathematical formulas, but to understand the essence, let's simplify everything as much as possible. And let's make a simple analogy by comparing the universe to an air balloon. Perhaps this is not the best example, but it's what we have at hand. First, we mark different parts of the slightly inflated balloon. Now, as we blow up the same balloon even more, we see that it increases in size, and the distance between all the marks increases. Note that the location of the marks doesn't change since only the surface of the balloon changes. Now, if we use our imagination and look at the situation from one of these marks, we see that all the other marks move away from it. This is roughly how the principle of the expansion of the universe works. Each galaxy is a mark, and the surface of the air balloon is the universe. However, the way expansion works on the surface of the universe, which resembles the surface of an inflated balloon, is a little strange and seems to contradict common sense. It looks as though the fabric of space is stretching over time, causing all objects within that space to be pulled apart from each other. The farther apart the objects are from each other, the more the space between them stretches and the faster they move away from each other. If the universe were filled with homogeneous matter, it would simply stop and become less dense, and each part of it would gradually move away from everything else. So, why do galaxies collide? The answer lies in the fact that the universe is a hierarchy. Galaxies located close to each other become clusters, which in turn form superclusters of galaxies. The expansion of the universe occurs everywhere uniformly and attacks on a large scale within one cluster of galaxies. Galaxies within a cluster are connected to each other by gravitational attraction and are relatively close to each other, at a distance of about a couple 100,000 light-years. Therefore, such objects can approach or move away from each other independently of the universal expansion, which leads to collisions between galaxies. Now, let's add another question on the same topic. It goes something like this. If the universe is expanding, why doesn't the distance between planets in our solar system change? Earth should be moving away from the Sun in this case, but this is not happening. The universe is not perfectly homogeneous, as there are regions of higher density, such as planets, stars, galaxies, and galaxy clusters. There are also regions of lower density, such as vast cosmic voids where there are few massive objects. Other physical phenomena besides the expansion of the universe dominate on small scales, comparable to the size of asteroids and smaller, including electromagnetism and nuclear forces. On larger scales, such as the size of planets in the solar system and galaxies, gravitational forces dominate. At the largest scales, comparable to the size of the universe itself, the main battle is between the expansion of the universe and the gravitational attraction of all matter within it. On the largest scales, expansion wins out. The most distant galaxies are receding so quickly that no signals we could send, even at the speed of light, will ever reach them. The superclusters of the universe, long thread-like structures along which galaxies are arranged, stretching for billions of light-years, are being stretched and pulled apart by the expanding universe. In relatively short timescales, they will disappear, and even the nearest galaxy clusters to the Milky Way, located just 50 million light-years away, will not pull us towards them, despite their gravitational attraction being over 1,000 times greater than our own. On small scales, expansion will drag us apart, while on larger scales, gravity will ultimately win. On larger scales, the expansion will triumph, and the Virgo cluster will remain gravitationally bound. The Milky Way and the entire local group of galaxies will remain bound and eventually merge under the influence of gravity. Earth will continue to orbit the Sun at the same distance, and its size and the atoms it's made of won't expand because the expansion of the universe only operates where other interactions gravitational, electromagnetic, and nuclear can't overcome it. If a force is strong enough to hold an object together, even the expansion of the universe won't be able to change it. The reason for this is that expansion is not an interaction, but rather a velocity. Space is expanding at all scales. However, The expansion only affects all objects together. Between 2 points in space, the space will expand at a certain velocity, but if this velocity is smaller than the escape velocity between 2 objects, if there is a force binding them, then the distance between them will not increase. There will be no effective expansion at any moment, as the expansion is overcome with a margin. Therefore, it will never acquire the cumulative effect observed between unrelated objects. Thus, stable bound objects can survive without changes in an expanding universe. Thus, an eternal cosmic battle is taking place between gravity and expansion, which has been ongoing for billions of years. Who will win? Write in the comments. Also, don't forget to hit the like button below this video and check if you have pressed the notification bell so as not to miss anything on our channel until our next interesting encounter.
Ripped to shreds in a flash, collapse in on itself? Or will it slowly freeze to death? Scientists are imagining the unimaginable. And they're coming up with some wild ideas about how it's all going to end. This is the end of the universe. A battle is taking place in the farthest reaches of space. No one can see it, but scientists are certain that it's happening, and that the outcome is grim. The universe is going to end. It won't happen for billions of years, but there is no way out. Figuring out how it will end is the challenge of astrophysicists around the world. They're pointing high-tech equipment out toward the heavens to unlock the secret of our fate. The possibilities are frightening. In one scenario, gravity pulls the universe back into itself, similar to air being let out of an inflated balloon. The universe goes back to its original size. This is the Big Crunch.
That'd be the end of the universe, and a big fireball, as all the matter collapses onto itself. That'd be pretty dramatic.
Then there's the Big Chill. The universe expands until the nuclear furnaces that power all the stars burn out. The universe grows cold and dies.
A second possibility is actually kind of sad. The universe will continue to expand forever, and it will just grow into an increasingly cold and lonely place as the expansion removes our nearest neighbors from us, and we just end up a single isolated community of stars and galaxies.
Then again, there could be a much more spectacular end in which everything is ripped to shreds, down to the last atom. Think of it like a balloon that is filled with too much air. It pops.
It's much more dramatic than the Big Chill, and just as fateful as the Big Crunch. The universe continues to expand, but at an ever-quickening pace. And in fact, the pace is so great that even the space-time fabric cannot hold the universe together.
However the end comes, it will be a dramatic conclusion. To understand how it all could end, scientists turn to how it began. The mystery starts to be solved here, at the Mount Wilson Observatory overlooking Pasadena, California. In 1929, while looking through what was then the world's largest telescope, Edwin Hubble makes a strange discovery. The universe is expanding.
Hubble's discovery led to a whole new picture of the universe, that it was a dynamic environment and that it evolved. It changed in time, and that's different from pictures that people had of cosmology previous to that.
Before Hubble, Scientists said that the universe was static and unchanging. Hubble's discovery that the universe is expanding meant it had a starting point, a beginning.
That brought the idea forward that, hey, what if we ran the film backwards in time and found the point at which that began?
The Big Bang. That fraction of a second when the universe and everything in it exploded into existence from a point smaller than an atom.
One common misconception about the Big Bang is that we can identify a point in space where the Big Bang occurred. But in fact, it's more appropriate to think of the Big Bang as a simultaneous creation everywhere of space, which is then continuing to expand to the present day.
Scientists theorize that at the moment of the Big Bang, the first small particles of matter called quarks were produced. They collided to form the building blocks of the universe. These floated in a thick fog of hot plasma for about 400,000 years. Gravity, also created at the Big Bang, drew the particles together, eventually creating the first stars and lighting up the cosmos.
The theory of the Big Bang is a very solid theory. What happened at the moment of the Big Bang is still something we're working on. We don't really understand.
If the universe has been expanding since the Big Bang, scientists must consider that it will stop expanding at some point. The question is, how? The most obvious answer involves gravity. What goes up must come down. Stars and galaxies and everything else might reverse direction. The universe would collapse in what some scientists call a big crunch.
Take the top and then see the other handle and just jerk them apart.
A model rocket offers clues to how the big crunch would work. The rocket is like the universe expanding into space out of the Big Bang. An initial bang allows the rocket to overcome the pull of gravity.
5, 4, 3, 2, 1.
Eventually, when the fuel is exhausted, the rocket coasts a few feet higher, stops, and is pulled back to Earth. This is what would happen with a big crunch. The entire universe is essentially pulled back to its launch pad.
The universe itself has its own momentum, its own energy. It's moving outward. But eventually, there's a point where possibly the universe will stop that moving outward, just like the rocket that we saw, and have to fall back in upon itself and collapse again under the force of its own gravity.
In this scenario, the universe could return to its original state just before the Big Bang, setting the stage for a perpetual seesaw of creation and destruction. The Big Crunch theory moved to a scientific back burner. Cosmologists figured out that there must be some form of energy that keeps the universe from collapsing. The existence of such a force leads to new theories about what the universe is made of and how it might end. And evidence about how this might play out is found in some of the most powerful and mysterious phenomena in the cosmos: black holes. Predicting how the universe will end involves some of the most advanced technology known to man. On a remote volcano on the island of Hawaii, astronomers are monitoring a battle in space that is shaping the fate of the universe. At an elevation of nearly 14,000 feet, the Keck telescopes bring astronomers from all over the world nearer to space for a clearer view of the cosmos. They come here because the telescopes work best far away from city lights and as high as possible above Earth's polluted air. Harsh conditions make it difficult to work here, but for scientists in pursuit of the great mysteries above, it's paradise.
So this is a remarkable location, but of course the air is very thin, it's extremely hard to work here, but these telescopes are amazingly powerful. But we're ambitious astronomers. We don't just stop looking at easy objects. We try hard to look at the very faintest objects so we can understand the extremities of the universe.
Here, astronomers like Richard Ellis are working on a problem that has been all-consuming for cosmologists since Edwin Hubble. They know the universe is expanding, but what they don't know is how fast. It will be difficult to predict exactly how the universe will end until they solve this mystery. The answers lie in the past.
Now what I did the focus on was a V equals 12.
There it is, yeah. Okay, that's the dry star.
Get a better focus now, that was worth doing.
An astronomer like myself uses a ground-based telescope as a time machine. We're looking back in time to study distant galaxies, seen as they were a long, long time ago.
One of the distant galaxies that astronomers found revealed a powerful source of X-rays from something that they could not see. It was in the constellation Cygnus and emitted no light, but something was there. Whatever was emitting these X-rays had a mass about 7 times that of Earth's sun. There wasn't a name for it, so they called it a black hole. Black holes offer scientists an analogy to how the Big Crunch theory works. When certain stars run out of fuel, they collapse in on themselves into a smaller and far denser mass that attracts more and more matter, just like the Big Crunch. The gravitational pull is so powerful that anything that falls near a black hole will be forever trapped. Not even light can escape. It's a mind-boggling concept that something invisible is detectable and offers a view to our ultimate fate.
This black tarp represents space, and space is relatively flat. But when you put a massive object into space, it curves it. This is a penny, and notice how it comes into a really beautiful circular orbit. Basically, the black hole trapped it into an orbit around itself. And that orbit becomes very circular as it gets closer. And now the penny will eventually disappear, go inside the black hole.
Earth's sun warps space similarly to a black hole, only it's a cosmic wimp by comparison. The gravitational pull of our sun is much weaker. Earth and all its nearby planets are trapped by the sun's pull, but it's so mild that it just stays in orbit without being sucked into the sun. The mass of a black hole can be 1,000,000 times the mass of the sun, or more, causing a huge warp in the space around it that consumes everything that comes near.
That black hole wraps space around itself. And so if material falls near it, it falls inside and gets trapped forever.
Black holes exist in isolated areas throughout the cosmos. A black hole's gravitational pull is a scaled-down version of the force that could cause the universe to collapse. That force is dark matter, and dark matter is what scientists often call cosmic glue.
Hi, Matthew. So let's do some cosmology here. Dark matter attracts other objects via its gravitational attraction. It's a positive force.
There's another force that opposes gravity, and that is dark energy.
Dark energy, we don't really understand what it is, but it's a negative repulsing effect that pushes galaxies away from each other.
The whirlpool in Richard Ellis's demonstration represents the gravitational force of dark matter. The green dye coming out of the syringe shows how the stuff of the universe collapses under the force of dark matter.
The presence of dark matter acts as the focus for the gas in the universe, bringing structure together. This is how the Milky Way developed as the universe expanded. Little things merging into big things, the positive, constructive force of gravity. Now, if this was the only force in the universe would stop expanding at some point in the future, and eventually the universe would start collapsing. Gravity would eventually halt the expansion, bring it back together in a big crunch.
Yet the universe continues to expand and isn't showing any signs of collapsing. This suggests the opposing force of dark energy could be stronger than dark matter. But it will take scientific detective work to find out. They look to one of the most violent forces in the universe for clues.
We're studying exploding stars to try to understand if they can tell us the rate at which the universe is expanding.
These are explosions at the end of the lives of stars, not unlike our sun. The fuel that these stars have in their centers is spent. The star collapses, the outer part expands, and the star becomes something called a white dwarf.
White dwarf stars sometimes have other stars orbiting nearby, a companion star. A massive explosion could happen if the companion star's debris falls onto the white dwarf, causing a spectacular fireworks display in the cosmos. Scientists consider exploding stars, or supernovae, like in these images captured by the Hubble telescope, to be reliable telltales of how fast the universe expands. Their brief and bright explosions allow scientists to track the universe's expansion and give them a way to measure its speed.
Essentially, they are white dwarf stars that become nuclear bombs. They explode with a certain brightness and a certain length of time. It takes a certain amount of time for that brightness to dissipate. They are essentially standard candles. Any one of these will look the same no matter where it is in the universe.
Astronomers measure the distance and speed of these exploding stars by measuring the amount of red light they emit. The faster the star moves away from us, the redder its light appears. The expansion rate of galaxies containing stars like supernovae can then be used to interpret how the rest of the universe is moving outward.
We know this because we can compare the velocities of galaxies with their distances.
These are the clues that lead astronomers to answer just how soon the universe will reverse direction and come back together in a big crunch. Or, this information might lead to an entirely different conclusion. Dr. Ellis is looking at clues at the Keck Observatory in Hawaii. While the telescope is on the top of a huge volcano, he's in a viewing room on another part of the island.
Hey, emission lines, Johan.
Oh, you see it?
In the red side, I think.
At the same time, Johan Richard is at the California Institute of Technology in Pasadena, California, evaluating the light from a distant galaxy that the Keck telescope captured in Hawaii. He's looking to see if any of the known elements coming from the galaxy are in the red spectrum and moving farther away.
We can interpret that as a velocity, as how much the galaxy is moving away from us. We can really interpret how the entire universe is behaving, is expanding.
Interpreting redshift is the cornerstone of the quest to pin down the fate of the universe. Clearer pictures of the universe that have only been possible in recent years have led cosmologists to conclude that the redshift of distant galaxies is greater than predicted. This is startling. Not only is the universe expanding, it's speeding up. Nothing in the observable cosmos could account for an accelerating universe, and yet the data seem irrefutable. This has to mean that an invisible force is working against gravity. Cosmologists have come up with a name: dark energy.
So when the universe was young, gravity was the most dominant force. And so what we see here is galaxies as particles on the surface of the water bound together by gravity. And at a point about 7 billion years ago, dark energy and gravity are pretty well in balance. But the universe continues to expand, the density goes down, and so dark energy starts to take over. And lo and behold, the universe starts to accelerate. So dark energy is now the dominant property of space.
So the universe started out with a certain amount of energy, and we know we're trying to understand how much energy there is, and we know the universe is expanding as it moves outward with time. We also know now that the universe's expansion is accelerating, and we don't know, is that acceleration going to slow down or not? We're still trying to understand that. So in understanding what's going to happen to the fate of the universe, we have to know how much energy is there, how much matter is there.
The history of the universe is really a battle between dark matter and dark energy. These two forces are in opposition, and so both the history of the universe and its ultimate fate is really the competition between these two forces.
The Big Crunch theory was a result of scientists interpreting that dark matter is the dominant force, but astronomers now suspect that dark energy might be much stronger. If so, the end could be dramatic and violent.
It pulls apart solar systems, it pulls apart stars, and eventually it grows so strong that it pulls apart matter itself, breaks bonds, pulls apart atoms, and reduces everything to fundamental particles, and that's the end of the universe.
The battle between dark matter, the force that holds the universe together, and dark energy, the force seeking to tear it apart, has set the universe on a path of destruction. If dark matter is the victor, the universe might collapse. If dark energy rules the cosmos, it could rip to shreds.
The expansion grows so strong that it tears up the entire universe.
It'll be a strange twist of fate. Dark energy, the force that propelled matter to form a magnificent universe, continues to push it outward and drives it to its demise. To find out if dark energy is in fact winning the battle, scientists will first need to know how fast the universe is actually expanding.
The most remarkable feature of the universe is that it's expanding. Every galaxy is moving away from every other galaxy. When you look out into the night sky, you see distant stars, galaxies, clusters of galaxies they observe with telescopes, and they're all moving away from us. We can illustrate that with this balloon. As we expand it, we see that every dot drawn on this black balloon, like the night sky, is moving away from every other dot. But there's something else that we know about the universe, something else that we know about the expansion. That is that the expansion is getting faster. The universe is accelerating. The size of the universe is getting bigger at a faster and faster rate. And we don't know exactly how fast it's accelerating, but if it's accelerating fast enough, then something really dramatic could happen. The universe could end up tearing itself apart in a big rip.
This is perfect. This is great that you rigged this up. So this is a giant version of the demo that I do in class.
Dr. Robert Caldwell attempts an earthbound experiment to show how dark energy affects the acceleration of the universe. He uses a paintball gun mounted on a truck.
Yeah, and basically, I mean, we could adjust the angle in any way that you want it. What do you think about this?
I think down at the ground,
a little bit more
is the best, so we can mark each time the gun fires. That'll be good.
Let's try that.
He sends the truck coasting down an incline. Earth's gravity pulls the vehicle downhill, which is similar to how dark energy propels the universe outward, causing it to expand. Gravity pulls the truck forward at an increasing speed. The gun fires paint at the ground at regular 1-second intervals. Caldwell measures the distance between the paint dots to calculate just how fast the truck was accelerating. He'll use the data from this experiment to see how gravity's force compares to dark energy's force in the cosmos.
We started thinking about the Big Rip when it was discovered that the expansion of the universe was accelerating. The degree of acceleration is not known, and it's the subject of a lot of effort by astronomers today to try and figure out exactly how fast the expansion is growing. What is the past evolution of the universe in detail, and if we can glean from that, what is the future evolution of the universe? It's not known exactly how fast it's accelerating. There's some evidence that the acceleration is beyond a certain threshold, and beyond that threshold, there's a runaway effect that could take place, and it would rip apart the universe.
Good luck. Fantastic. I think we've got some good data.
Excellent. How do we measure this?
Great. Give you that end.
All right.
I'll take this.
5 feet 8.5 inches.
The point of the paintball experiment is to find parallels between the truck propelled by the invisible force of gravity and the accelerating universe.
I'm glad we got the long tape measure because it's really growing pretty fast, the interval.
Within a few measurements, the distance between the paint spots increases by nearly 7 times. If the truck were in space, at this rate, it would travel faster than 100 miles per hour within a minute, and over 1,000 miles per hour within 10 minutes.
They're getting big now.
Here we got 42.5 feet.
42, all right, 0.5.
The question for Robert Caldwell is whether the same kind of expansion and acceleration are happening on a cosmic scale.
What's the capsule made of? Is it plastic or something?
Gelatin.
Okay.
It's all biodegradable.
So
you could actually eat them if you wanted to.
This right here is the data that I took with Eric. The cumulative distance traveled by the car as a function of time, and that's beautiful. It's this nice parabolic shape. That's exactly what you expect for an accelerating body. Now over here I've got another calculation going on where I'm working out the acceleration of the universe.
Robert Caldwell's calculation shows that forces on Earth are similar to forces in space. This demonstration, then, gives a sense of the dramatic rate of expansion that appears to be happening in the cosmos.
By eye, it might be difficult to appreciate how good a fit it is, but I can tell you that the weight of the statistics indicates that an accelerating universe is a very good fit to this data.
If, like the truck, the universe is continually accelerating, then billions of years from now, the universe might tear itself apart.
All the distant stars and galaxies will be pulled away from each other. They'll be pulled away from us. But moreover, we won't have time to grow cold and lonely. It'll actually be pretty exciting and dramatic and violent. Stars are ripped apart, planets are ripped apart, and even atoms are torn apart before the universe ends. It wouldn't happen for at least 50 billion years, but still it's an interesting fate for the universe.
What would atoms ripping apart look like? Things like coffee cups are solid. Atoms join together to create something that will hold a cappuccino without leaking a single drop. Zoom in through the cup, like sailing through the cosmos, past the molecules and into the atoms. The solid cup is nothing more than a fabric of atomic particles that formed a bond to become matter. If these particles were to move apart, the bonds that hold this cup together stop working. The atoms no longer support molecules. The connections between the minuscule particles dissolve. Matter in the form of this cup ceases to exist. It disintegrates, gone from existence. This is the dramatic end that Robert Caldwell foresees for the universe.
What you would see if you were standing on Earth or standing on some other planet that happened to still be around at that time, you would see something that looks like a wall of darkness approaching you. And as the wall of darkness approaches, stars would go out, galaxies would go out, and then eventually that wall of darkness would surround the planet, and then pretty soon atoms themselves are torn apart, and that's it. Just the wall of darkness shrinks down to a point, and that's the end of the universe.
According to Robert Caldwell, that moment is still billions of years off, leaving plenty of time to refine the research.
In a way, this is like a detective story. We're trying to figure out what is the culprit, or who is the culprit responsible for the cosmic acceleration. We think we know its name. We call it dark energy, but we don't know the modus operandi. We don't know exactly how it works. And what's needed is more information about the physics behind the dark energy. We want to know exactly what it does and exactly what it's made out of. And in answering those questions, we'll be able to figure out exactly what is the fate of the universe.
The Big Rip is one theory. Cruising just above Earth's atmosphere and peering deep into space, the Hubble telescope provides scientists with clues to a less violent, but equally unavoidable, end of the universe. Scientists now say the universe is expanding, and that depending on how fast it is accelerating, it might end in a big rip where everything tears apart. It's also possible that it will continue to expand, but at a slower rate. The universe wouldn't rip apart, but would become dark, cold, and lifeless.
If dark energy turns out to be constant, a constant property of space, and continues at the same rate that it is now, the universe will keep expanding forever, and it will be a very sad state. I think in the end, it just chills out. Everything cools down.
Evidence for the Big Chill and all of the theories for the end of the universe, in part, come from the Hubble Space Telescope. It has been orbiting Earth since 1990 and has an unobstructed view of the cosmos. The extraordinary images it beams back to Earth are amazing in their clarity and detail. And because of Hubble, scientists can make better predictions about how the universe will end.
So here is an example of a very deep field that was taken by the Hubble Space Telescope, which literally you point the space telescope at a single region in space. And if you looked at this from a typical ground-based image before Hubble was launched, first of all, it's literally almost size of a postage stamp. And so suddenly, the first Hubble Deep Field that was ever taken had 4,000 galaxies that looked just like the galaxies here, that were never visible before from the ground. A tremendous power. Each of these smudges in their own right is another galaxy. Each one of these galaxies contains about 100 billion stars.
Hubble sees more than just stars and galaxies. It just might be on to one of the key ingredients of space, an invisible ingredient that could put the brakes on dark energy's effect and cause a big chill. That's dark matter. Scientists talk about dark matter as the substance that holds the universe together and could prevent a big rip. Evidence that dark matter exists is seen in some of Hubble's images of nearby galaxies. It sometimes appears as though other galaxies surround them. The other galaxies are not really there at all. Rather, they are reflections of more distant galaxies coming from behind. Astronomers suspect this optical illusion is dark matter causing a weird distortion of light called gravitational lensing. The light from the more distant galaxies is literally bent by the curvature of space caused by stars and dark matter in its path. The more dark matter there is between Earth and the distant galaxy, the more the light will be bent and the greater the force to cause a big chill.
The gravitational lensing is a tremendous tool for the astronomer because we can measure the distortion in background galaxies and use it to trace the distribution of dark matter on various scales. We're looking at a distribution of idealized galaxies here on the sky, and the light from these distant galaxies is passing through clumps of dark matter. what you look at is not really what's happening. It's a bit like wearing spectacles and not knowing that you're wearing them.
And if you can tell how much that bending is occurring, you can map the dark matter, and you can also see, well, if there's dark matter there, is the universe around that dark matter behaving the way it should given the gravity or not? If it's slightly gravitating less, then dark energy might be changing in those places.
Identifying which energy force dominates, dark matter or dark energy, will give scientists more confidence about whether a big chill or a big rip will be our fate. The best evidence shows dark energy as the driving force, but by how much? Solving this mystery depends on astronomers finding ways to measure how fast the universe is moving. On Earth, it's simple to determine how fast something moves. An airplane, for example, is relatively close. We can look at it and calculate its speed by estimating the distance it travels and timing how long it takes to get from one point to another. But a star's light can travel for millions or billions of years before it can be seen on Earth. By the time its light gets here, the star will be long gone, and it's too far away to gauge its speed or distance traveled with any certainty. The universe is expanding, only scientists cannot give precise answers about how fast. The mystery moves closer to being solved by imaging the cosmos with greater precision. Clearer images from space make it easier to estimate the rate of expansion.
If the universe continues to expand with time, then ultimately all of the energy sources, the nuclear furnaces in stars, would run out and die, and the universe would actually get very cold, and there'd be something called a big chill.
In the big chill scenario, Earth could become a lonely, cold planet as the universe expands. Distances between stars grow so vast that they nearly disappear from view. Over time, they burn out, and eventually the entire universe ends in a frozen state. This sphere demonstrates the principles behind a big chill. The marbles coming out of the sphere are like stars that were formed following the Big Bang. Dark energy propels the stars outward. Dark matter slows them down. In a big chill, the expansion would continue, but the nuclear fuel that causes the stars to burn will eventually run out. From Earth's perspective, the first thing to go would be sunlight. The sun dims as it exhausts its last bits of nuclear fuel. Earth would freeze and become lifeless. And billions of years after humans are gone, the cosmos expands out of view. A few newer stars might remain, but most would have long moved away. The furnace powering the universe burns out. The darkened universe continues to expand, a frozen and lifeless remnant of its once vibrant existence.
Eventually, if this keeps going, if nothing changes in the composition of this energy density, the universe will continue to expand forever. It's going to get colder and colder, and eventually even our neighboring galaxies will be receding from us so fast that we won't be able to see them. So the universe is going to get cold and dark, and it will be a very lonely place.
Astronomers have much to learn about the influence of dark energy and dark matter. And much of the newest information is coming from this probe in deep space. It's sending back information that's helping scientists to interpret the history and the fate of the universe. The night sky, by all appearance, is a quiet and peaceful place. But in reality, there are forces that are driving it to an end. Big science moves astronomers closer to deciphering the universe's great mysteries, including its ultimate fate. The solution to the universe's riddle may well be hidden in this multicolored image. What's incredible is that it's a map of the early universe from the moment it was conceived. And even more fantastic, it reveals a great story that helps cosmologists predict how it will end. The machine that captured this is called WMAP, a NASA satellite that's working around the clock to chart the cosmos.
What we're looking at here is the edge of the visible universe. It's the light that WMAP measured, it's the remnant heat from the Big Bang, and this is literally the oldest light in the universe that we can see. This fossil relic from the early universe tells us a great deal about what the composition of matter was like, what the expansion rate was like, and really what the conditions were at the birth of our universe.
WMAP is one of the great astronomical breakthroughs of the 21st century. Nothing before could give us such a clear image of the energy left over from the Big Bang, energy that scientists call the cosmic microwave background. WMAP is measuring temperature differences in the cosmic microwave background, which may finally make it possible to predict which force will dominate the universe and how that force will bring the cosmos to its end.
The blue spots are regions in the microwave light that was produced by the Big Bang that are slightly colder than the average temperature, and the red spots are regions that are slightly hotter than the average.
Temperature differences revealed by WMAP tell scientists about the nature of the matter and energy that is contained within the universe. They're able to analyze the light patterns and find clues not only about the substance, but also the fate of the universe.
We only capture a tiny part of the electromagnetic spectrum with our eyes, and we have to go to much longer wavelengths. The same wavelengths that are used to heat water in a microwave oven are what we're measuring here with WMAP.
WMAP is so precise that it can detect differences in temperatures as small as 1/1000th of a degree. This sensitivity helps scientists to calculate the ratio of dark matter to dark energy, forces that will determine how the universe ends.
We assembled all those difference measurements and make a map of what the variations look like. And by turning up the contrast, we can basically subtract off this uniform glow from the Big Bang and look for variation.
It doesn't look like much until Gary Hinshaw adjusts the contrast. Then the WMAP image comes to life. Looking at WMAP imagery is in essence taking a journey back through space and time so that we might get some new ideas on the fate of the universe. Pulling away from the probe and following the path of the light it is collecting, we pass Mars, Jupiter, and Saturn, whose reflected light takes over an hour to reach Earth. Then, leaving the Milky Way, we pass Andromeda, the next nearest galaxy, whose light takes 2.3 million years to reach us, which means we have traveled 2.3 million years back in time. And finally, we arrive back 13 billion years ago, at the beginning of visible light. Before that, superheated hydrogen gas is everywhere. WMAP can see this far back in history. It's confirming important facts about the universe and what's driving it to its demise. The final act for the universe becomes more easily predicted thanks to WMAP. Its information, combined with the work of astronomers, has led to some astounding discoveries concerning a rapidly expanding universe. Rapid expansion supports the dark energy theory and the possibility of a big chill or big rip.
We now know from all the data we've had in the last 10 years that there's, by a factor of 2 to 1, more dark energy than dark matter. So dark energy is the dominant constituent of energy in the universe.
The evidence seems clear. Dark energy is taking over and is leading astronomers into new thoughts about the beginning and the end of the universe.
Before the discovery of dark energy, things were a lot simpler. If we could determine the amount of matter in the universe, then we could say something about its ultimate destiny.
Those simple days are gone, but the proof is adding up and supports the idea that the universe will continue to expand. But will it do so to oblivion?
We've made huge strides over the last century in learning something about the evolution of the universe and its expansion. But we've now raised more questions in some sense than we've been able to answer. And so I think the next decade is going to be even more exciting.
Astronomers have tons and tons of challenges that have been thrown our way by theorists, and we are rapidly trying to figure out how to answer all of these questions. And I think that's the exciting future, because if you can go out and really observe something, you're testing it. And that's what science is all about.
The battle between dark matter and dark energy is expected to go on for billions of years, and humans will be long gone from Earth when the final outcome occurs. But no pursuit has been more significant to science than understanding how the universe arrived, how it works, and how it will end.
It's a never-ending quest. It's driving astronomy. What are the answers to these profound questions? The constituents of the universe, the nature of dark matter, and perhaps the biggest mystery of all, what is the ultimate fate of the universe?
From the drama of our planet's origins and the birth of our solar system comes one of the most startling revelations of modern science. The solar system we see today, quiet, stable, was once a battlefield. Newborn planets blasted through space, competing for stable, circularized orbits inside a grunge-style mosh pit of gas and dust. For those that find the right balance, the prize is survival. For the rest, world-shattering destruction. A new look at the chaos of creation and a frightening possibility in our distant future. Mars. The Curiosity rover is searching for clues about the origins of the red planet. It confirms the presence of oxygen and nitrogen isotopes hidden in the rocks and soil.
We use isotopes to try to figure out the history of planets, partly because they are immune to many of the changes, the chemical changes that occur when you have things like collisions and so forth. Isotopes, the relative abundances of these isotopes are like fingerprints.
Curiosity confirms a unique mix of isotope fingerprints. The isotopes indicate that Mars formed elsewhere in the solar system and moved into our neighborhood. Our solar system is full of oddities pointing to an imperfect birth and a malformed evolution. All of our planets go around the sun in the same direction that the sun is spinning. This is the same direction that the clouds within our original nebula began to rotate. 6 planets spin around their poles in the same direction. For them, the sun rises in the east and sets in the west. Yet two planets spin the opposite direction. For Venus and Uranus, the sun rises in the west and sets in the east. Uranus not only has a retrograde spin, it rolls on its side like a bowling ball. At Neptune, the icy moon Triton orbits backwards, opposite from the direction of Neptune's spin. Do these planets spin backwards because they were rocked by titanic collisions in the past?
So we see evidence in the architecture of the solar system for not only collisions like Earth's moon and the fact that Venus is rotating in the wrong direction and Uranus is on its side and so forth. All these things are attributed to collisions. We also see in the asteroid belt and in the Kuiper belt, the outer asteroid belt if you like, we see that the orbits of these things look like they've been disturbed.
Closer to home, our own Earth has an inexplicable 23.5-degree tilt. Its spin axis is radically misaligned from its magnetic pole. And our moon is comparatively large for a planet our size. Now, a new theory may be able to explain many of these oddities. It is called the Grand Tack hypothesis. Four and a half to 5 billion years ago, a gas giant planet arose inside a primordial disk of gas and dust.
Jupiter didn't just form where it is, but formed and then moved inward towards the sun.
As it spirals toward the sun, Jupiter herds asteroids and rubble.
Jupiter's natural tendency is to drift in slowly through this debris field that it's traveling around.
The inner solar system is also thick with gas and dust. The planetary system is well underway. Numerous worlds are born in this region, including the Earth. Primordial skies are ruled by chaos. Jupiter's approach destabilizes these planets. Their orbits decay into wildly swinging ellipses. Some are tossed out. Others fall into the sun. Their numbers are unknowable. These are ghost worlds from a bygone age.
Jupiter just causes all heck to break out in the solar system, and all that debris in the outer solar system gets flung inward towards the inner solar system.
And it was a busy time in the very early solar system, and since we're colliding with each other all the time,
and then it stopped. Jupiter's invasion of the inner solar system is mysteriously halted. The planet makes a turn, or, in sailors' parlance, a grand tack. Lurking behind Jupiter is a second gas giant, Saturn.
So as Jupiter was migrating inward, Saturn was following it and growing. And as Saturn was growing, it came to have a size that it had a gravitational impact on Jupiter, which became more important than the gravitational interaction between the gaseous disk and Jupiter. They reverse direction. And in a sense, you can think of Saturn and Jupiter feeding off one another and moving back out.
gravity tugs each passing planet.
Is exert a very subtle little periodic force at the right time, and you can have amazing changes in the motion of the object you're pushing on.
Once enough energy has been transferred, the planets synchronize their orbits. They are said to be in a resonance. For planets, resonances are achieved and maintained through the mutual push and pull of gravity through the fabric of space. They're a key factor in the continuing evolution of our solar system. This effect can be duplicated in the lab.
We have 10 metronomes here set up on a swinging platform. They have little weights on pendulums here, but they've all been set at the same frequency. And I'm going to try to start them as best I can, completely out of phase, randomly. So their oscillation is going to transfer energy by the swinging of this plastic sheet to the other metronomes that are out of phase to get into phase with the majority. It's inevitable that there's going to be some majority group which starts out swinging more or less together, and they are eventually going to win out. Just doing this as randomly as I can. Aha, maybe in this corner I see 4 that are pretty closely synced. Yes, now it's more like 5, 6. Now you have one that's almost completely out of phase. So every time the majority hits a beat, it's going to give a little impulse, a little push to the platform, and that push is transferred to the metronome that's not in sync. Because the platform, you can actually see this platform vibrating back and forth in sync with the majority of these metronomes. Working on this one. So we're pretty close to resonance right now.
As the metronomes achieve resonance, it's important to notice how the platform shakes.
Now, it doesn't have to just be the force that's being transmitted by the plastic platform. It could be a force at a great distance, for example, the force of gravity. Just these small, little, seemingly insignificant pushes building up over multiple cycles can have dramatic energy transfer. That is how planets do it.
Like the metronomes, the two gas giants form a resonance.
We don't know exactly how long that took, but we have some fiducial marks for timing in the solar system formation, and that means that the Grand Tack had to have occurred relatively quickly, talking hundreds of thousands of years, perhaps, to a million years.
The two planets retreat until they reach their current positions. The sequence of planets as we find them today is based on Jupiter and Saturn's orbits. The planets eventually achieve a sequencing that many students learn through a mnemonic, such as, "My very educated mother just served us 9 pizzas."
Was there a time when the mnemonic was scrambled? Seems very likely the answer is yes, not to mention a lot of additional letters were probably in there as well.
Jupiter's menace of the inner solar system is finally over.
If Saturn had not formed at the right time in the sufficient size, Jupiter would have continued migrating in, throwing out objects, unfortunate objects in the inner solar system, and ending up very close to the Sun where it would stay. Yes, the Earth would be gone. Or the Earth would have had a terrifying encounter with Jupiter and would have had its orbit changed dramatically to gosh knows what.
There is mounting evidence that Earth had a terrifying visitor. Not Jupiter, but
Theia was this planetary body that was roughly the size of Mars. And through this collision, a lot of particles were ejected, probably completely destroyed. We don't really know how much of Theia was preserved. probably completely destroyed. We don't really know how much of Theia was preserved.
Earth is rocked off its axis, its surface liquefied. Chunks of Earth's mantle are shoved into space. As a planetary body, Theia ceases to exist. Its remains are absorbed by the Earth and intermingled with the debris field. A new planetary body is formed, the Moon. Further evidence is found in rock samples from the Apollo moon landings.
This is a sample from the Moon, if you can see it. This was collected by the Apollo 15 mission.
Moon rocks contain isotopes identical to those found on Earth. When the Moon arose, it is first covered with a magma ocean.
People imagine the lunar magma ocean to be like this magmatic chamber I am describing, but at the surface and covering a whole planet. I see it as this ocean, like the Pacific, but this has to be like completely magmatic, orange, and like probably like fluxing around and probably moving.
Conditions in the lunar magma are as hellish as we can imagine. But a microscopic treasure forms in the magma: crystal zircons. These are the same gemstones used in jewelry. But the zircons in the Apollo moon rocks yield a different treasure.
So those zircon are very important because we know they crystallize in this lunar magma ocean. We know roughly when they crystallize in the lunar magma ocean. So they are one of these old pieces of the moon that we are looking for, one of these old pieces that we can use to date the origin of the moon.
Zircons not only give the age of the moon, they set a specific date for the collision.
The age of the moon is 4.51 billion years old.
4.51 billion years ago, Theia becomes part of Earth and forms the moon. But the story is not over. Space probes measure the moon slipping 3.8 centimeters further away each year. One day, the moon will break free. When that day comes, there will be no more tides, no more romantic moonlit nights. Could planetary orbits be inherently unstable? Could the chaos of planetary migration return? Haute-Provence Observatory, France. It's here that a discovery from a faraway star gives one of the biggest revelations about our own solar system. The story begins when Swiss astronomers Didier Queloz and Michel Mayor noticed something unusual about a star 50 light-years away in the constellation of Pegasus. Everything about this star is ordinary. A main-sequence, mid-life yellow dwarf, just like our Sun. But with one strange difference. The star at Pegasus 51 is rocking back and forth. It's a weird anomaly astronomers have never seen before. They check their instruments. Everything is working, including their new spectrograph, a device that splits the starlight from Pegasus into rainbow colors. Hidden inside the colors are patterns of lines. By tracking the day-to-day movement of these lines, astronomers make a startling discovery. Pegasus 51 has a planet. But no one has ever seen a world like this. It's half the mass of Jupiter, yet it's extremely close to its star. 9 times closer than Mercury is to the Sun. The planet at 51 Pegasus must be inside the corona, broiling in temperatures over 1,000,000 degrees Fahrenheit. Soon, another planet is found around another star, and then another, and another. Astronomers have now confirmed over 3,700 exoplanets beyond our solar system. Nearly all of them are Jupiter-class planets grazing their host star. They're a new, previously unknown type called hot Jupiters. They're so numerous, hot Jupiters challenge theories about the origins of planetary systems.
It's very difficult to make a planet close to the star because there isn't enough mass to build a giant planet very close to the star, and there's gravitational frustrations for trying to build a planet very close to the star.
Astronomy is shaken with a new revelation. Planets do not stay put where they're born. When they're big enough, they migrate. It's a process called planetary migration. And yet, our own solar system has no hot Jupiter. Astronomers realize the Jupiter in our solar system was once on the move as well, but its migration was halted by a resonance with Saturn. Pegasus 51 shows where a planet lands when its migration is not blocked. The strongest evidence for the Grand Tack hypothesis comes not from our solar system, but from exoworlds charted around other stars.
Planetary migration is a universal concept. We see evidence of it out there in extrasolar planets, other solar systems. There's no reason why planet migration shouldn't have operated in our own solar system.
The New Horizons probe finds evidence for roving planets within our solar system. While charting ancient craters on Pluto and on the surfaces of its moons, the science team discovered many craters are the same age. This suggests that they were formed by a single event. Even way out here, tiny Pluto was smashed by a wandering planet. The Pluto catastrophe may be related to other planetary migrations in the outer solar system.
It was noticed that the exact orbits of the giant planets, particularly the outer giant planets, the icy planets, Uranus and Neptune, can be explained by their migration outward. There's a point in time about 3.8 billion years ago where Uranus and Neptune trade. And it's because of what some of these mean motion resonance interactions that we were talking about earlier. So this mean motion resonance involving Jupiter and Saturn and so forth just causes all heck to break out in the solar system. Uranus and Neptune, all of a sudden at 3.8 billion years, they literally swap places, and all that debris in the outer solar system gets flung inward towards the inner solar system.
The disruption in the outer solar system causes a new wave of violence. Astronomers call this epoch the Late Heavy Bombardment. Much of the cratering we see on our moon today is from this period. It may be possible that swapping orbits with Uranus is how Neptune got its moon. Today, the epoch of planetary migration appears to be over. The solar system seems stable, but what does the future hold? Computer simulations reveal what may be the greatest threat to the solar system in over 4 billion years. It comes from a very special relationship between Jupiter and Mercury. Mercury's orbit is slowly perturbed, thanks to a subtle but constant gravitational nudge from Jupiter. A new resonance, like the one between Saturn and Jupiter, that saved the inner solar system, is forming between Jupiter and Mercury. In 2001, computer models for the solar system were run 2,500 times.
They plug in the positions and the orbits of all the planets in the solar system in a computer, and they just let it run through time, through millions of years, hundreds of millions of years, billions of years, to find out whether or not these orbits are stable.
Change the location of one planet, say Mercury, by 1 millimeter, and you find that that change will give completely different predictions about where everything is going to be millions of years in the future.
To see how quickly and easily things can change, we have only to go back to our metronomes.
All I have to do is stop this platform from moving so that it cannot swing freely. Now, there's no way for the metronomes to influence each other. They're good metronomes, but they're not perfect. They can't be going at exactly the same frequency in the same phase, and they're just going to fall apart because they have no way of forcing the others to go to resonance.
The same applies to planets. Any small change can disrupt their harmony or restore it.
Now that the platform is free to swing again, it can again transfer energy and sync them up just like we saw the first time.
Scientists want to understand the consequences of a destabilized planet Mercury. In one case, Mercury leaves the solar system. The loss of its gravitational pull disrupts the balance of both Venus and the Earth. Earth and Venus swap orbits. The superheated atmosphere of Venus cools. Massive rains pour onto the face of the desert planet. Oceans arise. The land cools. And the air thins. Even the remains of an ancient visitor begin to cool off. Venus becomes like Earth. But the reverse happens to the Earth. As Earth settles into Venus's orbit, temperatures rise. The air becomes unbreathable. Glaciers melt. Oceans boil. The sun looms larger in the sky, only to be obscured by a thickening cloud cover. Suffering will be great, but brief. The entire 4 billion year pageant of life is cooked in a matter of days.
Complete and utter destruction and elimination of all life on Earth. I'm not just talking about higher life. I'm not just talking about civilization, but everything. A sterilization of the planet is something that I would want to think about a bit.
Sterilized, uninhabitable, and quiet. There is another possibility, equally dark and apocalyptic. A runaway Mercury is deflected by the gravity of Venus and barrels toward the Earth. It may be a frightening encore to the opening act of our solar system. The equilibrium of the ages is over. If this scenario is correct, Mercury crashes into the Earth, just as Theia did 4 billion years ago. The question is, could it happen today? Or is it a fate far away in the future, at a time when mankind itself is but a distant memory?
The problem is that even with a perfect computer that understands all of the laws of motion perfectly, not just gravity, but all the other subtle forces that go into it,
you cannot give it accurate enough initial information about the locations, the masses, the sizes, the speeds of all of the objects in the solar system.
Odds are, we may never see such a calamity. And yet, among the billions of stars in our galaxy, how many worlds are on the move? How many will share this fate?
Checking out traffic this morning along the Kewy Gardner, Guy Valentine.
It's a bit of a battle for drivers without cover. I'm talking if you don't have any shades, you're fighting some pretty bright sunshine.
Also caution on Highway 7 going eastbound.
And northbound Don Valley Parkway on the ramp to eastbound 401. We've got a disabled vehicle.
June the 14th, 2002. It was just another busy workday with all the usual hustle and congestion. With all the close calls and near misses that people all over the world have come to accept as the normal level of risk in everyday life. But on that day, high overhead and behind the sun, what no one saw coming, what no telescope on Earth was able to see against the blinding light, was an asteroid big enough to destroy an entire city. From behind the sun, asteroid 2002 MN came hurtling towards Earth, faster than a speeding bullet. It shot past, less than a third the distance to the moon, and nobody saw it, until 3 days later, when the rock emerged from Earth's shadow into the night sky, going away.
It looks like the Earth just dodged a bullet. Actually, it was an asteroid. Scientists say it blew by last week at a distance they describe as a close shave.
The airline industry would call this a near miss. Scientists who study asteroids and comets called it a problem.
The threat of asteroid impacts on the Earth is very real. We know that throughout history this has happened. The craters we see on the moon are examples of the kind of impact history that the Earth has had. But it also happens very rarely. So it's a very unusual kind of hazard. It's a hazard in which the risk in any one year is very low, but it does happen, and if it really did come about on our watch, it could end civilization.
These cosmic bullets originate on the far side of Mars, in the main asteroid belt, where a bracelet of celestial debris circles the sun. Millions of rocky fragments, building blocks of a planet that never quite came together when the solar system was formed. What's often depicted as a busy cosmic junkyard is actually more like a big empty speedway. The rocks are far apart and moving very fast, ranging in size from pebbles to boulders to rocks the size of Mount Everest. Occasionally, the tug of Jupiter's enormous gravity drags an asteroid off course, causing it to crash into another asteroid. Some veer away into new orbits that cross the paths of Mars, Earth, Venus or Mercury. Another ring of debris called the Oort cloud is the source of most comets, which are big, rocky ice balls that orbit the sun and cross the paths of the inner planets. All the inner planets and our moon bear the scars of numerous asteroid and comet impacts.
We do get hit all the time by pieces of debris from asteroids and comets. In fact, 40,000 tons of cosmic debris plummets into the atmosphere every year. We see them every night as shooting stars. They don't hit the Earth very often, but when they do, clearly it isn't just going to be a matter of a shooting star seen in the sky. So it is inevitable. It's only a matter of time before the next big one hits us.
Even small rocks can make a big impression. In 1908, about 2,000 square kilometers of Siberian forest were instantly flattened. as an asteroid exploded near the Tunguska River. The impact site was so remote, researchers had to mount a wilderness expedition just to find the place. When they arrived, there was no crater. Paintings, based on eyewitness accounts, described a fireball. A horrendous explosion in the sky.
Didn't actually come crashing down to the ground. It exploded maybe 5 to 10 kilometers up in the atmosphere, and that made a big blast wave in the atmosphere, and that is what did the damage.
All this was caused by a relatively small asteroid, somewhere between 50 and 100 meters across. Roughly the same size as asteroid 2002 MN, the one we couldn't see coming. Tunguska's 2,000 square kilometer blast wave would have leveled London. But as bleak as the thought of cosmic collision may be, there is at least a glimmer of hope.
One of the special things about the asteroid impact problem is that unlike the weather or earthquakes or other natural hazards, we, at least in principle, we could do something about it.
And when we know one's coming for us, our claim is that the technology is available today to stop it.
On the Earth, we've got active geology, we've got volcanoes, we've got earthquakes, we've got continental drift, we've got rain, we've got wind, we've got storms, we've got snow. All of those things erode away craters, and that, in some ways, actually fools us into thinking that indeed the Earth doesn't get hit as often as it actually does.
Counting craters on the Moon and then estimating how often the Earth gets hit can be a pretty sobering exercise. One scientist who made that kind of calculation was astronomer Ernst Öpik, who published his impact estimate back in 1951. The general public, however, paid little attention to the science or the implications. But one individual who did take the issue to heart was Lembit Öpik, the astronomer's grandson, who got himself elected to Parliament.
My grandfather is the reason why I carried on in politics, what he initiated in science. In essence, he was a pioneer. He saw the danger of asteroid and cometary impacts with the Earth, and he had the courage to speak up about them. And he did that at a time when it wasn't really taken seriously, in the 1950s and 1960s.
After years of pushing and prodding, Lembit Öpik convinced the British government to commission a comprehensive scientific study of the asteroid and comet threat. The expert conclusion was, the threat is indeed real.
Now, the government has set up a task force to examine the risk of an asteroid hitting the Earth.
Still, skeptical politicians might want to get on the bus and take a trip to the Natural History Museum. Ask any schoolchild who's been there recently, and you'll hear a fascinating and truly scary tale about what happened to the dinosaurs.
The dinosaurs were alive here. They were dead when this sediment was deposited, and this layer is one of the most unique layers in Earth history.
In 1980, the discovery of iridium beside a layer of clay which marked the end of the age of dinosaurs led Lewis and Walter Alvarez to publish a theory that a huge asteroid or comet had hit the Earth 65 million years ago and wiped out the dinosaurs. But for this concept to be confirmed, there had to be a crater. There may be tons of dinosaur bones in these dry canyons, but where on earth was the big crater? Just the kind of mystery a budding young scientist would love to solve.
When I went back to...
Off the coast of Mexico's Yucatan Peninsula, Dr. Alan Hildebrand investigated a huge gravity anomaly discovered by oil drillers back in the 1950s. Put that together with a semicircular magnetic anomaly, and you get a massive crater, 180 kilometers across, near a little village called Chicxulub Pueblo. Most of the crater is underwater now. Erosion and continental drift have covered the visible evidence. But 65 million years ago, this was ground zero.
this object would have fallen through the atmosphere in just a few seconds. It's going through the sky, it would have been brighter than the sun. As soon as it contacts the surface of the shallow sea in Chicxulub, of course, it starts propagating the shock wave down into the planet, and it keeps pushing into the planet, and it only gets stopped maybe about 30 kilometers down. The pressure wave would have traveled around the entire planet in the atmosphere. You could have heard the impact on the other side of the planet. The giant impact fireball rising out of the hole, it would have risen, say, 10,000 kilometers above the surface of the planet. Near the impact site, it would have been so hot, it would have evaporated the clouds and been hot enough to make the forest, even a green forest, begin to burn.
For Alan Hildebrand, finding that crater pretty much clinched the argument. Planet Earth had been all but sterilized by a rock the size of Mount Everest.
3/4 of the species of large animal life went extinct.
We have made the case. We've got the qualitative information and we've got the statistics to show that there is a very serious risk.
If you wanted to save planet Earth from cosmic disaster, where would you find people with all the right stuff to do the job? Well, Houston, Texas might be a good place to start looking. This town has that rarest of breeds, the space cowboy. Houston is home to NASA's Johnson Space Center, where rocket science is a way of life and astronauts learn their trade.
If you could roll me 90 and then go down, I'll come in on my side.
Behind a swimming pool big enough to swallow an apartment block, you'll find a small research lab where the rocket engine of the future is being built and bench tested.
Yeah. Very nice. Question is, how big is the plasma going to go from here to here?
Dr. Franklin Chang Diaz is one of the lead researchers, as well as an astronaut with 7 shuttle missions under his belt.
And in fact, there was a time in one of my flights where we got hit by very tiny micro meteorites, perhaps, or some sort of orbital debris, which made little tiny dents or little craters in the windows of the shuttle.
First-hand experience with rocks in space gave birth to a new idea and a dual purpose to Chang Diaz's work here. His rocket engine has been developed for long-distance missions to Mars, or as far away as the icy moons of Jupiter. But it could also be used to push a dangerous asteroid out of harm's way.
I am concerned enough to think that we need to not waste time arguing about it as to whether it's real or not. I think we need to move ahead. If this is a threat which has a very low probability, all it takes is one, and we are history.
But before we can send a spacecraft chasing after a rogue asteroid, we have to know where to look for it. In the American West, if you drive across the desert to the White Sands Missile Range in southern New Mexico, you'll find the most powerful and effective asteroid hunter on Earth. Scientists here have tested everything from rockets to the very first atomic bomb. Today, across the valley floor from the Trinity bomb site, the US Air Force has installed one of the world's most advanced telescopes. This state-of-the-art technology was developed by MIT's Lincoln Laboratory as part of the Star Wars anti-missile defense system. These may not be the world's biggest telescopes, but they clearly are the best when it comes to finding deadly rocks in space. This is LINEAR, the Lincoln Near-Earth Asteroid Research Facility.
On a given night, when we scan the sky with this, we'll find perhaps 10 to 12,000 moving objects in the sky. Now, most of those are main belt asteroids, and as such don't represent any danger to Earth. But on the other hand, something like half of those will be brand new discoveries, and buried in there will be 1 or 2 near-Earth objects.
Because the Earth rotates, the sky is always moving overhead. To get a clear picture of an asteroid, you have to make the sky stop moving. And you do that with a telescope that can track or follow the stars. This way, you can take time-lapse pictures that isolate the blur of fast-moving asteroids against a crystal-clear sky. It then records these pictures like a TV camera on a computer chip that has 20 times more detail than the picture you're now watching. The LINEAR computer deletes previously known stars and planets, leaving a less cluttered time-lapse sequence of the new discoveries. At the end of each night shift, LINEAR's thousands of new discoveries are emailed to the International Astronomical Union's Minor Planet Center at Harvard University. A team of only 3 scientists must cope with the avalanche of new sightings, searching for potentially hazardous asteroids or comets. Computers make a rough calculation of an asteroid's orbit, but it's up to Brian Marsden to estimate the level of risk.
They may be reporting 50 or 60,000 observations from one night, and it takes a while to get through that. But so we look first at the fast movers and see if there's anything interesting there. H is equal to sine delta. We do sometimes get close to 70 or 80,000 observations a day, almost 1 per second. There are some days when we effectively have 1 observation per second.
Even with fast computers, Marsden's team can make only a preliminary calculation of each asteroid's orbit. 5 shots in one night cover only a tiny segment of an asteroid's orbital path.
You can't solve for the orbit completely from that, but the fact that you're seeing motion over a half an hour or an hour, something like that, does allow us to get a partial solution for the orbit.
Refining the orbit gets complicated. When 2002 MN shot past, its trajectory was warped by Earth gravity, and scientists at NASA's Jet Propulsion Laboratory in Pasadena, California, had to add that to their calculations.
Here's an animation I put together of the asteroid last year, which was discovered after it passed by the Earth.
An elite team of mathematicians and celestial mechanics is now working full-time on a computerized warning system.
Our orbit animation, you can see how when it returns out to the asteroid belt, the close approach to the Earth has changed its orbit, and it's no longer returning to the same place it started.
Because 2002 MN will circle around the Sun and come past us again, the NASA Orbital Mechanics team will have to adjust the calculation in order to know whether it will ever pose a danger to Earth at some point in the future.
So here we've zoomed in on the Earth-Moon system and we're looking down. You can see how close it came to the Earth. It went over the top. And how you can actually even see the bend in the trajectory. So it's a great example of how a close approach to the Earth, or in fact any planet, can be used to, or can significantly change in orbit.
To know where an asteroid is likely to be in the future, you need a model of the solar system. Mechanical models that show the relative motions of the Sun and planets have been around since the early 18th century. They're called orreries. What the celestial mechanics at NASA had to do was create a new digital model. One that includes the gravitational attractions of all the planets and the Sun. and all the other forces that can affect where an asteroid might go.
You just compute what forces are acting on this particular asteroid from all the planets and many of the minor planets in the solar system, and then we can actually trace the motion of that object around the solar system for hundreds of years.
For scientists, the acid test of their mathematics came when a strange new comet raced toward Jupiter. A stream of cosmic bullets that would shock and amaze millions here on Earth. In the spring of 1993, the eyes of the world turned almost in unison towards a doomsday rock like no other. From the far side of the solar system, it flew in a death spiral toward the largest planet. Gene Schumacher, his wife Carolyn, and their colleague David Levy had discovered an odd-looking streak of light that turned out to be a fractured comet. 21 large chunks of icy rock and cosmic dust heading towards Jupiter.
We knew we had something very unusual. It was so unusual we were a little unsure just what we were dealing with.
NASA asked Paul Chodas and his team to calculate the orbit and predict whether this new comet would actually hit Jupiter.
And it started off at some 60%, and before long it was 90%, and this was a year before impacts. As the impacts approached, we continued to predict not just the impact probability, which went very high, but where and when the comet fragments would hit the planet. And it was a prediction months in advance, and as we got closer and closer to the impacts, I kept wondering, well, is the math right? Will this actually happen the way it was predicted?
A giant comet is on a collision course with Jupiter.
Everybody on Earth who was paying any attention wanted to see if the comet would actually hit Jupiter.
We have liftoff of the Space Shuttle Endeavour on an ambitious mission to service the Hubble Space Telescope.
NASA's Hubble Space Telescope set its sights on the planet, and the pictures of what happened next were truly stunning.
Right there! Get it! Wait. Oh.
And then the impacts occurred. We were within minutes of getting the right answer on the time of impact, and the location of impact turned out to be just right.
Over the next week, 20 more fragments of the comet crashed into Jupiter, some leaving scars as large as the Earth.
Bang on its cosmic schedule, the comet's first impact was recorded by NASA within the last hour.
When fragment G slammed into Jupiter, releasing an amount of energy equivalent to about 6 million megatons of TNT.
In the wake of SL9, a group of concerned scientists gathered in Italy for a brainstorming session.
Hello.
They created a brand new international organization called the Space Guard Foundation.
Okay, I'm going to join.
To promote the discovery and study of near-Earth objects.
Some people imagine that there are lots of astronomers out there scanning the sky looking for incoming comets and asteroids, and that, of course, is not true. In fact, until recently, there was hardly anyone out there looking.
It's going to glow for about a half an hour and set everything on fire around you.
But whose job is it to defend planet Earth? Weapons scientists from the United States and Russia had already held a series of meetings and came up with their own ideas about how to deal with the impact threat.
Blow off some material, you get a reaction in this perpendicular direction.
The military establishment under Star Wars had created a whole lot of devices, or at least concepts, for weapons in space and devices in space. And in the early 90s, when the Star Wars program was looking a little bit iffy, I think there was some motivation for them to try to apply their technology to this newly discovered hazard from asteroids and comets.
The military approach to the problem proved to be controversial. The notion of sending nuclear weapons into space generated an immediate backlash.
Edward Teller was proposing that we blow up an asteroid to show that we could protect the Earth. And I thought that was a pretty crazy idea. Blowing up an asteroid with a big bomb has a lot of problems associated with it, violating treaties, taking a single asteroid and making a swarm of smaller asteroids. It seemed like it was more interest in bombs than it was a serious interest in defending the planet. For NASA, on the other hand, NASA obviously is the natural agency to discover the threat and the objects, but they say, no, planetary defense, that's a military obligation and not an obligation of NASA.
Not NASA, not the military. Just when it seemed planetary defense was nobody's job, a tiny speck in the sky would set off doomsday alarms around the world. On a winter's night, the 6th of December 1997, a dim streak of light moving through the constellation Cancer was captured by a telescope in the Arizona desert. Big enough to destroy civilization as we know it, asteroid 1997 XF11 seemed to be heading towards Earth. The initial sighting by the Kitt Peak Observatory in Tucson, Arizona, was relayed to the Minor Planet Center at Harvard University in Cambridge, where a computer made the first rough calculation of the orbit. They were pretty sure it would miss the Earth on this pass, but it would be coming round again, and it looked like there could be a problem in 30 years.
There were indications of close approach to the Earth in 2028, like 25,000 kilometers, which really was rather close.
With only a handful of sightings, the orbit calculation remained very rough. It was hard to tell where this rock was going. So Brian Marsden posted a bulletin asking astronomers around the world for more observations before the rock became too faint to see.
I was saying, hey, get your big telescopes onto this. On one hand, we're only going to be able to observe it for another month or so. We want to improve the orbit calculation and find out exactly how close it is coming.
But one line in the bulletin said that the chance of a collision was small, but it was not entirely out of the question. Within hours of the website posting, reporters discovered XF11, and doomsday headlines screamed around the world. Because the close approach in 2028 would put the asteroid nearest to Europe, London newspapers focused on the exact moment life on Earth might possibly end.
Pictures of it on the internet show it as a tiny moving blob. Scientists have calculated its path in the year 2028.
Watch very carefully. September, October the 28th, the two coalesce.
But at NASA's Jet Propulsion Laboratory in California, the orbital dynamics team thought there must be some mistake.
The asteroid's orbit was affected by it. To my great surprise, when we ran our software, it said that the probability of impact of this particular asteroid in 30 years was essentially zero.
As it turned out, the end-of-the-world asteroid would miss the Earth. That big rock in space posed no threat after all. A frantic hunt through the archives at NASA had turned up photographs of XF11 taken 8 years earlier.
And as soon as those were placed into the orbit determination process, they confirmed the fact that there was no chance that it could hit the Earth in 30 years.
The public at large was not understanding uncertainty in this. They wanted, an immediate answer. Is it going to hit us or not?
But people were paying attention. One side effect of the false alarm was that public and political awareness of the threat had been raised. 2 months after XF11, new hearings were held in Washington, and NASA was told to speed up the science of asteroid detection. Finally, it seemed, there was a political will to do something. Congress gave NASA a 10-year deadline to search the skies and get a fix on the largest of the doomsday rocks. They called it the Space Guard Survey. While astronomers geared up to search the skies, Hollywood was going into overdrive.
I would go to every dinner party and I would say, are you aware what would happen if a comet was actually on a collision course with the Earth?
Oscar-winning screenwriter Bruce Joel Rubin was hard at work on the remake of a sci-fi classic. The new film, called Deep Impact, would be a Steven Spielberg production.
An army of scientists work desperately to build this giant rocket, this modern Noah's Ark, to carry a few picked survivors of our doomed civilization.
I think the thing that was hardest for me was the realization that people would have to be chosen to survive.
Let's take the ship away from them! Come on!
Probably a very, very small percentage of human beings would be left on the Earth able to survive something of the intensity of the comet that hit and destroyed the dinosaurs. So I felt making this movie is not just a mission to tell a good story, it's to change minds. It's to let people go, this is something real. This can happen to us. This movie is a wake-up call. It's not just a Hollywood movie, it is pointing at you.
As Hollywood released Deep Impact, telling the world in no uncertain terms that cosmic collisions were no longer just a cosmic joke, real-life professional asteroid hunters were making movies of their own. But instead of using cameras, they worked with delayed Doppler radar. Take the same technology behind a police radar system, jump the power to 400,000 watts, and you've got NASA's Deep Space Network, with huge multi-dish systems, like the Goldstone tracking station in California's Mojave Desert.
This is the main room of the pedestal of DSS-14.
The first time radar astronomer Stephen Ostro bounced a signal off a rock in space, a wobbling blot of pixelated data bounced back. What looks like digital gibberish spoke volumes to Steve Ostro.
Radar really does three things at once. One, it works at long wavelengths, so you're sensitive to structure on large scales and metal concentration. The other is you can make pictures. And you can't do this from the ground in any other way. You make pictures of objects, and then we take a sequence of pictures, and we go through a computational process to produce the 3D models. That's the second thing. The third thing is that it makes very precise measurements of distance and speed.
When the 1,000-foot radar dish at Arecibo in Puerto Rico bounced a beam off an asteroid called Castalia, the data was translated into a 3D computer model. The very first radar movie showed how Castalia spins and revealed that it was actually two massive chunks of rock held together by weak gravity. Every time they made the trip to Goldstone for a new radar target, Ostro and his team were like kids reaching into a box of chocolates. They never really knew just what they would find. Asteroid Cleopatra, shaped like a dog bone, was roughly the same size as the state of New Jersey and was made almost entirely of metal. Echoes from asteroid Tutatis produced images of a rocky, cratered surface and a wobbling, tumbling spin.
Every single one of these objects that we've made a shape model of is very different. This is Tutatis.
From a telescopic smudge of light to a 3D shaped model, radar gave them physical details and the first clear idea of what asteroids are really like. In the year 2000, the radar movie crew developed a dark and mysterious new image, asteroid 1950 DA, a big rock that gave everybody a bit of a shock.
Once we got the radar data, we began the normal process of just seeing how far in the future we could predict this thing before the uncertainties in the orbit blur out. And in this case, we could go over 880 years into the future. And what was startling about that case was the impact probability turned out to be non-zero.
Non-zero means there is a chance this rock could hit us. On March the 16th, in the year 2880, 1950 DA will cross the Earth's orbit. Will it hit us? The odds? 1 in 300. If 1950 DA does hit the Earth, the most likely point of impact would be at sea. Of all the big asteroids discovered thus far, this is the most dangerous one we know. Eric Asfaug and Stephen Ward have created a computer model of the impact.
Yeah, it's kind of funny how this started. It was with the movie Deep Impact, and I was getting phone calls. Lots of people were getting phone calls about the movie, whether it was accurate, the big cresting tsunami coming across.
The concept here is that this asteroid, which is about 1 kilometer across, will hit the ocean at 17,000 miles per hour, and it'll blow a hole in the ocean about 19 kilometers across and all the way to the bottom. And so when this huge hole of water gets blown into the ocean, the water will run back in again, and it overshoots and it collapses and overshoots many, many times, and each time it pumps out a wave. So it starts out hundreds of meters high, comes ashore on the coast of North America at about 50, 60 meters. Up toward Canada, Grand Banks, it's about 40 meters. 20 meters here in the coast of South America, and about 15, 20 meters all the way over to Europe. These waves would run inland about 4 kilometers. So pretty much everything within 4 kilometers from the beach would be covered up repeatedly. And so we'd pretty much be wiped away like you're scrubbing the floor. You know, just scrub like this, and it's pretty much we'd all be carried back out.
In February 2001, a NASA spacecraft called Near Schumacher made the first ever landing on a chunky, pockmarked rock named after the Greek god of love. Asteroid 433 Eros is 33 kilometers long and 13 kilometers wide, one of the largest near-Earth asteroids. The pictures were spectacular. The data will take years to process. Proving that they could land on an asteroid was a major achievement, but in the end, they still don't know much about what's inside. How dense? How tough? How brittle or crumbly is it? What would happen if they gave it a good shove? The surface appearance of any dark and mysterious object can be very deceiving.
So these two spheres, as far as I can tell, have exactly the same mass, the same compressibility, the same color. If I were a spacecraft orbiting these, and these were asteroids, I'd be very hard-pressed to tell which was which. Yet, if I dropped them from a height, and only one of them bounces, really illustrates the fact that one of these responds elastically, and one of these responds like a lump of clay. And it's critical to really go and find out what's inside before we even start thinking about moving these things around.
When a 3D model of the asteroid Castalia got smacked in a computer simulation, a problem occurred. An impact with the same energy as the Hiroshima bomb turned Castalia into a pile of rubble, but did not deflect its trajectory in any significant way. But there are other ways to apply force to deflecting an incoming asteroid. Using the power of the sun to push dangerous rocks out of the way may not be so far-fetched after all.
This is a typical near-Earth asteroid. Its name is Galevka. It's about 1/2 kilometer across. It's a hazardous asteroid. Its most likely fate is going to be to strike the Earth someday, thousands of years from now.
Modern-day researchers like Eric Asfaug say the idea of a giant orbital magnifying glass to burn space rocks could work.
You create a vapor plume in one direction, and that starts the asteroid moving in the other. It's a very gradual process. It's not going to happen instantaneously. You need to know where this guy is 100 years or 50 years ahead of time. But if you do, you've got all the time in the world for a satellite to sit there, no human intervention whatsoever, and it'll gradually shove the asteroid into a different orbit, and it'll miss the Earth.
Some of the technology to do this already exists. Take an inflatable parabolic antenna the size of a tennis court, convert it to a solar collector, and use it to focus sunlight on an asteroid. The Russians have built and are testing a giant sail that captures the minute pressure of sunlight. Just attach the sail to an asteroid and let the rock hitch a ride to someplace else. But using the sun to save the Earth means waiting for nature to do the work. If we don't see an asteroid until the last minute, solar power would be too little, too late. A nuclear electric plasma engine could push an asteroid out of harm's way. The rocket technology at this NASA lab in Houston, Texas, could provide the power for a space tugboat. A group of astronauts and aerospace engineers is designing the B612 mission to prove that asteroid deflection can be done with existing technology.
These are rockets that have very tiny amounts of thrust, but they are so frugal in the use of propellant that we can keep the rocket going for periods of the order of a year.
Building a better rocket engine is only the first step. Figuring out how to latch on to an asteroid, point it in the right direction, and push without losing control is the really tricky part. After years of research, NASA finally had it. The first complete draft of a plan, a demonstration mission, to save the planet.
We can move the asteroid off the impact with the Earth 10 years later so that it misses the Earth, and not just miss it randomly, but miss it very precisely so that we don't simply pass on the problem to our grandchildren.
Midway through 2003, the Space Guard survey had reached the halfway point. A little more than half of the kilometer-sized near-Earth asteroids had been located, and the news was mostly good.
For the 60% that we have already found, I can tell you that there is not a single one that poses a danger. For the 40% that we have not yet found, I can tell you nothing. One could hit tomorrow. Not very likely, but until we've found them and cataloged them, we won't know.
But finding the really big asteroids, those 1 kilometer monster rocks capable of ending human civilization, is only the first part of the challenge. There are an estimated 50,000 smaller asteroids that are big enough to cause tidal waves or destroy vast regions of the Earth.
A 200-meter asteroid happens maybe once every 10,000 years, but that's like 600 megatons to 800 megatons exploding in one place.
Recall the small 60-meter rock that exploded over Siberia in 1908? Well, even though it could have destroyed a city like London or New York, rocks that small are not included in the current Space Guard survey, meaning no one is officially looking for them.
Which, of course, is the same thing as saying that chances are enormous that a Tunguska-sized object will find us before we even see it coming, as happened in 1908. That is likely to happen nowadays, that we won't see it coming.
There has been talk of expanding the search to include smaller asteroids. It'll take more and bigger telescopes and, of course, more money. But until we do, we'll have no idea where those city-killer rocks are.
Evolution on Earth has proceeded in part because every so often a global catastrophe comes along, pushes the reset button, and new things happen.
It wiped out the dinosaurs 65 million years ago, and at the time, we mammals were just furry little creatures burrowing around in the ground, and an asteroid or a comet impact took out our principal competition.
I guess we are saying implicitly, if not explicitly, that we want to do away with that natural cycle.
We've had enough evolution. We like ourselves on the top of the ladder. And we can do something which will change cosmic evolution from this point forward in terms of life on Earth.
Dinosaurs ruled the Earth until a big rock wiped them out. The question is, will another rock do the same to humanity?
Let's get a couple good pictures here.
Humans are the first species with the potential to block a doomsday rock and switch off the evolutionary reset button.
People very often say, look, you're just a doomsayer. You think that these awful things are going to happen. I'm not that way at all. I'm entirely optimistic. The way in which I view asteroids and comets and the possibility of them hitting the Earth is that it's a great challenge. Thank goodness we've realized the hazard and the danger before the next one happens. It's given us time, we hope, to do something about it.
Scientists can study the sky and find the dangerous rocks ahead of time. Astronomers can do the math and predict the orbits. People have the desire and the right stuff to do the job. There's a whole new field of science that could give humanity an option the dinosaurs never had.